let's talk about why we even need this statistic, okay? You've all had this experience in your life because all of you have been through K through 12 schooling, right? Or I assume, I'm making an assumption here, right? All of you have been through K through 12 schooling at some point in the United States. And we do a lot of standardized testing. There's the big tests, right? Like that everybody thinks about, like the SAT, but there's actually standardized testing throughout. Little milestone, and they're not little, but they're milestone exams that you take, sometimes to progress from one grade to the next, sometimes like at certain developmental milestones in like especially elementary school, stuff like that. All of those things, all of those tests that you've ever taken, all of the big ones, were never on a 100-point scale. They weren't ever like the test that you took in a class where, you know, it added up to 100 and your grade was real easy, right? It was always on this really odd scale, like maybe out of 68 points, or maybe out of 1,000, or maybe like out of 2,000 or 5,000. And so your score wasn't always easy to interpret. How do we compare these things? How do you compare your score on one exam and your score on another exam if they're not standard grades? If you take a test in here and you get like a grade out of 100, and you take a test in biology and you get a grade out of 100, then you can easily compare them. But what if their scales are not the same, right? Like in these real life examples where a 92 out of 100 is great, but a 92 out of 2,000 is not great. So we have to have some other way of comparing these scores. That's where z-scores step in. And what z-scores allow us to do is they allow us to take this weirdo test score and then standardize it and take this one on its weird system and standardize it. And now that they're both standardized, we can compare them. And so it's a lot of the practical use of z-scores is about comparing scores to a distribution that's been standardized so that we can make sense of them. So that's why they exist, right? What's on the slide, of course, is that if I just tell you a raw score, it means absolutely nothing. So if I told you, hey, I got a 25, well, if it's out of 25 points, that's amazing. If it's out of 2,000, that's terrible. I need other information besides just the raw score. When I have that z-score, that's what allows us to better understand where a single score exists in relationship to all of the rest of the scores in the distribution. But then it also would allow us, if we had other scores, to compare them, because again, we've standardized them so that they're in the same type of distribution. So again, why do we use them? I've kind of said all this, right? It's so we can make comparisons and we can better understand where a score is. So how do we do that? It says here, right, z-scores allow us to compare because we've standardized it. We've standardized it on the same shape. So I'm going to insert a slide here and just draw it for you. And you've all kind of seen this probably at some point, and this is a rudimentary version of it. This is the normal curve. The z distribution is basically the normal curve. The average or the center, right, of that distribution is going to be at 0. And then each of our standard deviations, our SDs, right, all of these are going to be each at 1 point increments. So the first ones would be plus and minus 1, and the next ones would be plus and minus 2, and then plus and minus 3, and conceptually so on and so on and so on. What that means is that we've got a way to mark where like the bulk of the distribution is, and then if we wanted a certain percentage, we could mark more of that, right? Because again, it's all standardized. But every time I take a number and I put it onto a z distribution, what I have effectively done is moved it to a distribution where the average is always 0 and each standard deviation is always at 1 point. And then the shape stays the same. And again, that way I can say, oh, you know, like a score here, I can compare it to a score here and I can know what that means, okay? Okay, that's what a z-score does. Now, once I do that, right, each z-score tells us 2 things. It'll have a sign, positive or negative, and then it will have the number itself. So like if I had one here on the thing I just drew, right, let's say I put one right here, and I tell you this is the z-score is like plus 1.25. Again, there's a sign there, positive or negative, and then there's a number, 1.25. The sign tells us whether or not that score exists above or below the mean. Positive numbers are above the mean, so that would mean that that score is higher than the average score for the distribution. And negative numbers means that it is below the mean, so that score is lower than the average for that distribution. Again, in our example of, positive 1.25, I know that that is a score that's higher than the rest of the distribution's average score. Then we also have the number itself. And again, the number 1.25 in this example, right, tells us the distance away. So I know, right, from the fact that it's positive that it's going to be above the average, but how much above the average? Well, 1.25 means that it's at least one whole standard deviation away and then a quarter of the next one. So it's there. If I said it was -2, I would know that it is 2 standard deviations below the average, right? If I said it was +3, it's, 3 above the average. Positive, let's say 0.5, right? Then it's just half a standard deviation above the average. The sign tells us the direction, right? Above and below, right? And the number tells us how much, how far away. So, of course, there's a way to calculate those. Now I can do the division easily if it's an easy number. So what this says is that the original distribution, right, that I'm transforming the score from, its average was 20 and its standard deviations were every 4 points. And this score that I've made up was, it should be here, is 18. Well, 18 is just 2 points away from 20, which is half of 4. Which is how I instantly know that it's 0.5. That's because I can do that math in my head. But if you if you can't do this math in your head, do not panic, right? Instead, we have formulas that we can use. Now, just to go ahead, since the exam is coming up, and to relieve some of y'all's concerns, you do not have to memorize formulas in this class. They will be provided in the exam. I think there's only like 2 exceptions to that. And I will always highlight on the study guide which ones I don't give you. And yes, you're absolutely allowed a scratch sheet of paper. I would encourage you to have a scratch sheet of paper. You get a scratch sheet of paper, a pencil, and a calculator that doesn't connect to the internet. So these 2 formulas that I have for you for how to find a z-score, you don't have to memorize these, okay? These would be in the exam itself. You just need to know how to use them correctly. Now you'll see there's 2 of them. Right? And the 2 of them, the difference is some of the mathematic shorthand. So this mu symbol is the symbol for an average, and capital M is also the sign for an average. The difference is whether or not we're talking about a population or a sample, but they're the exact same if you read them out. It's X, which is the score, minus the average, population or sample average, divided by the standard deviation. So they're the exact same. It's just the only difference here is whether or not we're talking about a population or sample, and that's why they look slightly different. But once you get your mathematical shorthand kind of memorized, then you would read these the exact same. So I've got just a little example here, right? If I tell you that the average score is 86 and the standard deviation is 7, and that your particular score that you're interested in was a 95. Find the z-score for that. Well, first of all, before I even get started, I know it's positive because 95 is greater than 86, which means the score I'm interested in is greater than the average. But then I just plug and play. So I take X, which is the score I'm interested in, which is 95, and I subtract the average score for this, which is 86. And when I do that, 9. And then we divide by the standard deviation, which in this we were given as 7. And when you divide 9 by 7, right, you get this number and some more, like it keeps going. So if I was going to just round that, we get positive 1.29, okay? So the math is not necessarily complicated math. It's some subtraction and some division. It's just a matter of knowing which ones go where and when do I use it. We can also have times where I want to find the raw score. Well, I can actually use algebra to flip that whole formula around the exact inverse to find the X. So there's a formula to find the Z and there's a formula to find the X. It's just which one am I being asked for? So if Dr. Wolf says, hey, I need you to find the Z score for this, you find the one where it's Z equals. And if Dr. Wolf says, hey, what is the raw score that goes with this? Then you use the X. But again, all it is just plug and play here, right? So for this one, it says raw score X equals mu, which is mean, plus whatever is that Z score times the standard deviation. So if I give you these things, and again, I'm going to give you this stuff, right? So you're going to have the formula and you're going to have the numbers. You just have to know how to plug them in and use them, okay? I'm interested in what was the raw score that went with this Z score. So I've got 40, right, is our average, and we're going to add together this Z, which was 1.5, and we're going to multiply that by the standard deviation, which is X. The key here is I have to do this part first, the multiplication part first, because that's the order of operation. So going back to that PEMDAS, we have to do multiplication before we do addition. So that's why the next line is 40 plus 12, because 1.5 times 8 is 12. And then that's how we get 52. So the raw score originally for this example was 52. I want us to do one that is more of a word problem as some examples. So I have both of your formulas up here, right? The one for finding a Z and the one for finding an X. And then we have this paragraph. So let's go through this. It says an instructor gave an exam to a psychology class. For the exam, the distribution of the raw scores has an average of 75.5 and a standard deviation of 10. The instructor would like to simplify the distribution by transforming all of the scores into a new distribution where the average is 85 and the standard deviation is 5. So a student who originally earned a raw score of 88, what is their score in the new distribution? So let's slow this down. So this, you all have probably been in a class where a professor has had to curve an exam. You can do curves two ways. You can do them what is the easy way, which is you take however many points the highest grade is from the top possible grade. So, you know, if you have somebody who scored like the highest grade was a 90, right? Instead of 100, you add 10 points to everybody and that kind of shifts everybody forward. That's the easy way to do it. You can actually do it mathematically, which is you move them all into a new distribution where you take everybody's old scores and you turn them into Z scores and you apply those Z scores into new scores. So that's possible. You can do that. So that's what this question is asking, is basically this instructor gave an exam, not so happy with the distribution, wants to apply it to a new distribution. And so if you originally earned an 88, what is your new grade? The reason why this one's hard is because you have to do both of the formulas. So step one is, and I'm going to write these out for you because we're going to do these in order. Step one, we find the Z score for the raw score of 88, okay? And then step two would be to apply that Z score to the new distribution to find the student's new score. So that's what we're doing here, okay? So step one then is I have to find the raw score for 88. And I'm going to pause. I'm going to let y'all work on that one and then I'll work it through you. So what are we doing here? So the first thing, like I said, is we need to find what a raw score of 88 is, and we're in the old distribution, so we have to use these older numbers first. And we're going to just plug and play what we've got, right? So again, our raw score is 88. Our average is that 75.5 because we're finding what the Z score is for that old distribution, and then we're dividing by 10, okay? First step is I have to resolve the stuff that's on the top. So 88 minus 75.5, right? That's 12.5 divided by, again, 10 is our standard deviation. It's positive 1.25. The way we know it's positive is that 88 is greater than 75. So that's our Z score. So then what we have to do is, again, that's your score. Let's say you're the person who earns the 88. That is your Z score. That is Amanda's Z score for her 88 in that weirdo class, okay? But the instructor, right, wants to do something else, right? Doesn't want that distribution, wants to make that distribution a little nicer for people, right? Do a little bit of a curve. So this is their new distribution. New distribution is going to have an average of 85 and a standard deviation of just 5. So in step 2, I need to take that z-score and find out what your new grade is. We need to take that new z-score that we just found, the positive 1.25, we need to apply it to the new distribution to find our new raw score, right? So we're going to use the other formula and plug and play for that one. I'm going to copy our other formula, and what we've got again to plug and play are that new distribution the professor wanted was going to have an average of 85. The z-score we just found, so positive 1.25. And we have to multiply that by the new standard deviation, which is 5. And again, I have to do the multiplication part first, right, in that PEMDAS order of operations, which is 85 plus 6.25, which gets us to 91.25. I think everybody in this class would rather have the 91.25 than the 88, but they are the exact same spot. The 91.25 is exactly the same distance away from the average of 85 as the 88 was from 75.5, okay? So while the number may look better, may feel better, all of that kind of stuff, they actually exist in the exact same place in the distribution. What we use this for, we can use it for comparisons, and that also helps us find out if something is noticeably different. So if I tell you, right, like the average person in group 1 has a score of, you know, negative 3.5, and group 2, person number 2 is a 0.5, then I know that person number 1 is way different than everybody else. Person number 2 is pretty close to the average. It's not even a whole standard deviation away from the average. But person number 1 with their negative 3.5, they have scored woo far away. So it helps us to compare, and then it helps us find scores or groups that are noticeably different. This comes into play a lot with hypothesis testing. We can use z-scores to understand probability. And this graph here, what this means is if I know that with that normal curve, that half of the distribution is in one side, that would mean that half of it is in the other side, right? Because again, it's symmetrical. I can say you have a 50% chance of winding up on the right and a 50% chance of winding up on the left. Again, because the curve is perfectly symmetrical, so there's a 50% chance that you're on the positive side and a 50% chance on the other side. Now, someone who has way more time than you or I, we're like, okay, well, yeah, but what would it be for each of the standard deviations? And someone's already done that math and can tell you, again, the probability or the percentage chance that you would wind up in any particular standard deviation. So what you see is if I wanted to be in that third distribution, right, between 2 and 3, it's only a 2.28% chance. That to be here is very extreme. That's kind of like the extreme tail then. We know that the bulk of people are going to be between the first two ones. They're going to be between -1 and 1, because 34.13 doubled is 68.3. So there's a 68% chance that you wind up just in this block here. That's the bulk, right? 68% is right there. If I'm going to say, hey, what's the chance of getting one of these two tails? Well, if that one tail is 2.28, then the other tail is 2.28. There's only a 5% chance that you're going to be in the tails. But I can also tell that just by looking, that normal curve bulges in the middle. See how it bulges there? That bulge tells me that there's going to be more stuff right here in the middle. Some of you probably saw that I said that there was only a 5% chance of getting in those extreme tails. I can actually use this for hypothesis testing. This is a similar graph. What it means is these extreme tails are where significant results are. And that if it's in this middle, it's 95% of the distribution, that means it's just like the average. And so when we get to hypothesis testing, I want you to remember this, because what it means is that we can come up with the probability of being in the tail, and we can do that by a z-score as well. So if I take a score and I turn it into a z-score, if that z-score is some of these numbers, at positive or negative 1.96, positive or negative 2.58, positive or negative 3.30, are statistically significant. So again, if I am doing either comparison of groups and inferential statistics, or if I'm just looking at one score to try to see if that one score is statistically different, I can just transfer it into a z-score and know. There's actually a whole chart, because again, somebody who had way more time than you or I said, well, could I do that for like every possible z-score? Could I find like what is the proportion in all of these tails? Could I do that? Wouldn't that be fun? And they actually built a whole chart where you have all of these numbers and all of that kind of stuff. Some versions of this class have you using this chart. I'm not going to have us do that. What I want you to be able to do is use the formulas and to conceptually understand z-scores. If you end up going into certain fields, you'll do a lot more with z-scores and you'll get a lot more training on like that chart. There's a chart like that for all of us, the statistics that we'll use. And so I'm going to have us use the other ones and get practice with those, because they're much more related to the stuff that you'll do in like 4100. So I have a slide in there just to remind you that the chart exists, but we're not going to use it, okay? And then once you understand these things, like I said, that's going to help you when we get to the first module after the exam for understanding hypothesis testing. Okay, so that's our video lecture on z-scores. If you have any questions at all, you can always email me, especially as you go through the practice problems that are in the module and the other videos and the textbook. When you get to the homework, if you have any questions, you can always email me as well. Otherwise, I'll see you online.